Alright, in this experiment we're going to do the Fischer Esterification. I have the reaction mechanism on the board. Again, I don't have it the way you need to have it in your lab book. You have to have all of your steps balanced. I'm going to turn off this noisy ice maker. Okay. Alright, so we're taking our glacial acetic acid. Alright, so there is your acetic acid, or ethanoic acid, and we are also going to add sulfuric acid, and then we're going to add N-propyl alcohol. So we are going to add all three of these together, and we're going to reflux it for 1 hour. So here is the reaction mechanism. Your glacial acetic acid, which is a concentrated acetic acid, is going to take the proton from the sulfuric acid. Alright, and you should show all of your bonds, you should show all of your lone pairs. I do not show all of my lone pairs on the oxygens. You should show those in your lab write-up. Alright, and so, and again, I'm not balancing the reaction. Every reaction has to be balanced when you're doing the lab. Alright, so you now have your acetic acid that is protonated, and it's protonated on the oxygen that has the double bond. Now you have 3 resonance structures here. That is one of the resonance structures. I did not include the other 2 resonance structures. You will need to show the arrows, the electrons moving, to give you the other 2 resonance structures. So there is a total of 3 resonance structures. There is one of them. You will have to give the resonance structures for that. Now note, when you're doing a resonance arrow, it is not a reaction. It is simply a resonance structure of the exact same thing. Alright, and so it's just showing the delocalization of the pi electrons. Alright, and so it is not a single-headed arrow. It is a double-headed arrow. It is a single arrow with a single line with arrows pointing in both directions. That is indicating a resonance arrow. Alright, so you take one of those 3 resonance structures that are all the same, and I'm going to take the one that we wrote up on the board, and that is going to react with your alcohol. In this case, we used N-propyl alcohol. And so the electron pairs of your oxygen attack the carbonyl carbon, and if you have your resonance structures correct, one of them will have a positive carbon here. That carbon is very positive, and so the electrons from your oxygen come and attack that very positive carbon. In one of the resonance structures, it is a full +1. Alright, and then the electrons go to the more electronegative oxygen, and you have your structure right here. Alright, and now this structure is going to lose a proton, and so you can show your H plus falling off, and that is fine, and that's how I have it. The electrons go to the oxygen, and when you have your product, it is simply an H plus as a product, or you can remove that hydrogen using the HSO4 minus can take that off, reform sulfuric acid. That would be another way to do it. You could have one of your alcohols take the H off. There are many ways that you can show to remove that H. I'm going to just say it comes off. And then in the next step, it's going to go back on. And so you can pick either one of the OHs, and that oxygen attacks that H plus. Alright, so when you are finished, then you have your reaction here, but this is where your product is, and you see that your hydrogen, and I wrote a little arrow here that says that these 2 things are tautomers, because in this structure your hydrogen is on the bottom oxygen, making that a positive oxygen. And all we did was we moved that hydrogen, and we could have moved it to either one of those other oxygens. They are exactly the same. All right, and so when you move the hydrogen from that oxygen on the bottom to the oxygen on the right, and all we did was move an H. The H plus came off and then it went back on. And that is called a tautomerization, and those two structures are called tautomers. So when you move an H plus from one spot to another spot in a molecule, those are tautomers. And that is then a tautomerism. So when you're writing it out step by step, a tautomerism is, in this reaction mechanism, going to be step 3, the H plus comes off, and then step 4, the H plus goes on. And so it is a two-step process. The H plus comes off, the H plus goes back on. All right, and so now we have water, and which is a good leaving group, and so the electrons come down from the oxygen of the OH on top, forms the carbon-oxygen double bond. You cannot have 5 bonds to carbon, and so that kicks out the water. All right, and so you have your structure here, and now I'm going to show the HSO4 minus. You should show it in its Lewis structure form that we got from step 1, and we're going to then get our product, and we're going to regenerate the sulfuric acid. Again, I don't show that. You have to balance every reaction. I give the organic products. All right, and so that is our N-propyl acetate. That is the product of this Fischer esterification. All right, so the overall reaction. So here's the overall reaction. You take your carboxylic acid. In this case, we used glacial acetic acid. You take your alcohol, and in this case, we used N-propyl alcohol. And we used sulfuric acid as the catalyst. So this is an acid catalyzed reaction to form our N-propyl acetate, and you also get water kicked out. All right, now if it were not a mechanism problem and a what is the product, a nice method is the lasso method. Again, the lasso method is not a mechanism. It is a method that you will then circle what is going to be kicked out. And so your carboxylic acid loses the OH, and your alcohol loses the H. You can see that in the reaction mechanism if you look again. All right, and so that is your water. And so when you circle the water and then you push together your CH3, C double bond O, and that's now connected to this O, CH2, CH2, CH3, you see that that is the product. And so if it is a problem on a test and it just wants the product, the lasso method will get you to the product very quickly. If you have a time test and you have to write out this entire mechanism to get the product, you will not have enough time to finish that exam. All right, so there's going to be 1 or 2 problems that you have to write out the full mechanism, and there's going to be 20 problems where it's going to be give the product. All right, so you need to know all the mechanisms, but you also need to know how to get to the product quickly. And that the best way to do that is to know a lasso method. All right, so we're ready to start our experiment. And you will be happy to know that in step 1 it says to reflux for an hour. Well, the reflux has been going for an hour, so we're not going to watch this thing on the video boil and condense. So here is our reaction right here. Not very exciting. It's a clear colorless solution that the solvent front is going to here, and then it's dripping back down. We have a boiling chip in the bottom. All right, and so what I've added to this, I already told you what I added, and this is how much. So I used a 50 ml round bottom flask, and then we have water going in the bottom, out the top, to make this nice and cool. And so as this boils, then it condenses and then comes back in. That is then a reflux. I added 7 milliliters of N-propyl alcohol, so 7.0 milliliters of N-propyl alcohol. I added 10.0 milliliters of glacial acetic acid, and then I added 1 milliliter of the concentrated sulfuric acid. All right, so when you're doing your limiting reagent theoretical yield, you only have to use the alcohol and the carboxylic acid. Those are the reactants. You do not need to put in a catalyst. It will never be a limiting reagent giving you the theoretical yield. So it's only the reactants that we need to go to see how much product can be formed. All right, so that's the amounts that we added in there. Now we reflux it. It's been going for an hour, so we're ready to start the next step. And that is to get this into a distillation. And so we are going to convert our reflux into a distillation, and then we're going to distill the liquid over to the right side. And I have an ice-cooled collection flask ready to go for that as well. All right, so I just wanted to show you what the distillation or the reflux look like. I'll get it closer. It's not much to see. It is simply the flame boiling the solution. The solvent front is about there-ish, and then it's coming back down and dripping in, and this has been happening for an hour. Again, it's not going to go dry because the liquid just goes right back in. It is not going to go out through the top. All right, and so that is a reflux, boiling without losing the solvent. And so now we have our next step. So I will remove the heats. I will get this ready for a distillation. So this is a simple distillation, and the only reason why they call it a simple distillation is because we are not going to do any sort of fractional distillation where you would need a larger, you would need two condenser tubes, one that goes up and then one that comes over. This is just a simple distillation that we are going to collect in a 250 milliliter Erlenmeyer flask that is iced up, and so that when we get our product over here, it does not evaporate. So we have it nice and cool, so it's going to stay in there. All right, so I usually start on the left side. I know what the level needs to be. It needs to be here to collect the liquid. All right, and so now I'm ready to get my condenser connected over here. All right. That's going to go there. A little bit of engineering going on here. All right. Alright, so now I got to get this to match up here. Alright, I gotta connect this one up. Now we are connected. Now we gotta, we're connected. reaction here is very important to make sure that is nice. This one is less important because it's just going to drip into this nice cool flask here. And then we put in our thermometer. That is sealed nicely, and then our water through. So going in the bottom out the top, so that stays nice and cool. This seal is there, and now we're ready to reflux. Reflux, ready to distill. We'll just reflux for an hour. We're done with that. All right. All right, so we're going to get this boiling. We're going to see what the boiling point is. But this is going to boil over all the unreacted starting materials as well as the product, and then we're going to have to separate all of our different components using our separator that is ready to go right here. All right, and then it has sulfuric acid, and you can see a light tint. If you heat it too much and it's got concentrated sulfuric in there, you're going to get a nice brown, black color. All right, so we are getting some solvent front going up and condensing. It's in the condenser. And first drip is there, first drip. And your temperature is at 40, 60, 80, 92 degrees Celsius. So the first drops are at 92 degrees Celsius. All right, we don't want to boil too fast so that we don't want any liquid being shot up through there. We want the vapors to come up, condense, and go down. So it is looking pretty good. Might be a little bit fast on the heating. Alright, let's see where we're at now. Alright, now we are 40, 60, 80. We're right at 100 degrees Celsius now. The higher boiling stuff might need a little extra heat, so I'm turning up the heat here to make sure that we get a consistent dripping over here. It's looking pretty good. Now we'll check the temperature again, and we are at looks like 104 degrees Celsius. The scale on that thermometer is very difficult to read. All right, so now we're getting some color here, and that is because, again, when you heat sulfuric acid, it's going to turn brown. And so once we have distilled over our product and our reactants, we're going to be left with our sulfuric acid that when you heat up your sulfuric acid, it's going to turn a color. And so usually a dark yellow, brown. If you heat it too much, it'll be black. Alright, let's see what our temperature is now. We are at 109 degrees Celsius. Alright, and so the residue in the distilling flask is just a few milliliters. We're getting pretty close to, it's just a few milliliters left here. So we're going to end this pretty quickly. See where we're at temperature wise. We're at 114. And we're getting that concentrated acid down here. It's getting thicker and thicker, and with heating it, it's all right. Now we are at 120. So at 120, we're going to call it good. We're going to stop the distillation at 120 degrees Celsius. Again, if our yield isn't ideal, it doesn't matter. We're just looking to get some product, and we're not looking for 100% yield. Okay. So we have this in ice water. We're going to add some saturated sodium carbonate, and so we are going to neutralize the acid. We know that there was sulfuric acid as our reactant, as a reactant. It was a catalyst actually, but we added it. Catalysts are added, so we added a acid, and there was nothing that was supposed to happen to that acid. We should still have the acid, so we need to neutralize it. And so we're going to add saturated sodium carbonate, and we should see some bubbling, release of CO2 gas. And once we have neutralized our acid, we are going to then transfer that to the separatory funnel and get our product separated from our aqueous level. Turn off the water and disassemble. This is pretty warm. There. This is some of this. All right, so this is the part we need. All right, so nice, clear, colorless distillate, but we know it is going to be acidic, and so this is ice cold, so the reaction doesn't go too fast. Pliers to get the lid off. There we go. All right, and so we should see some foaming, release of CO2. There's some bubbling going on. Not a whole lot of bubbling, so we may have left most of our acid over there in the distilling flask. We only added about a mil, and there's about a mil left over there. But there was some bubbles when it first went in. There's still a few bubbles going. It's just very, very minor amount of bubbles. You're not gonna be able to see it probably on the video. All right, and so after we added some of our sodium carbonate, we're going to test it with litmus paper to see what the pH is. So we want it to be neutral or basic. We do not want it to be acidic. And so I will get a little sample of this and see where we're at. Still red. Add some more. Few bubbles. See where we're at now. Still got a red tint to it. We haven't neutralized it yet. Might be a little feel thing like in there too. I saw a little pink. All right. Oh yeah, I see pink. All right, so we're going to know when it's, so when this solution turns a light pink, we're going to know that it is where we want it to be. So nice to have some phenolphthalein. That makes for a nice magic trick. You add 2 colorless solutions and then it turns pink. Amaze your friends. Now I don't have to worry about the litmus paper. I can just worry about a light pink color. So we're looking for a light pink. I know we have phenolphthalein in there. Bottle of sodium carbonate. This one might be a little more concentrated. All right, well, we'll test. I thought it would be pink by now. Litmus paper. Still red. Phenolphthalein doesn't lie. I have to add some solid sodium carbonate. Oh, there we go. So now we are neutral. So we have a green color. I don't know if you can see the green, but now we are neutral. So, so we are good to put it in the separatory funnel. Stopcock closed. Alright, now hopefully all that solid sodium carbonate doesn't clog up the separatory funnel. Probably should have decanted. Alright, I'm going to go with the deionized water rinse. Alright, so I'm going to then separate my two layers. Okay, so we're going to remove the lower layer as completely as possible and wash the N-probe acetate layer with 10 mils of water. Alright, so we want the top layer, we do not want the bottom layer. We're going to see if we clog this up. So the solid is not going to go through. We're going to need a new separatory funnel. Should have decanted that there. Solid in there this time. Alright, so much less solid this time. And we're using some more deionized water to make sure we get all in there. Alright, give it some time to separate. Hopefully it will. Still solid, but it is a much smaller amount. Hopefully this small amount will pass through. opaque bottom and the nice clear top is a good visual for where the product is at. And when it gets down here, it's nice and narrow, and the separation gets better and better. So you should clearly see, I'll get it a little closer. So you should clearly see the two layers. You got the clear colorless product layer on top, and then you've got your aqueous layer on the bottom. All right. All right. All right, so once we have that, we're going to wash with about 10 mils of water. Doesn't need to be measured because it's about, we'll just go ahead and stick in about 10 mils. Right on the mark. All right, so if you ever add your wash solution and you don't get two layers, well, you kept the wrong layer. All right, we have our two layers. Pick it up this time and bring it to you instead of. All right, so you've got your two layers, and now they both are clear colorless because we got rid of a lot of that solid sodium carbonate. All right, so that's that. Let it separate, take the lid off. All right, so right now it is cloudy. We have to give it a minute to get the nice two layers, and then take off the bottom layer. And once we have done that, we're going to put that with 2 grams of magnesium sulfate. So while that's going, I'm going to weigh up 2 grams of anhydrous magnesium sulfate to get rid of all of the water. Alright, so I got the 2 layers here. Big bowl. Not sure what's going on there. Try that again. See if we can get a little bit better of a separation there before I do that. We got 2 grams. Get a beaker beaker ready. All right, 2 grams of magnesium sulfate. So this is just to get rid of the water. You don't need to write down the actual mass. So about 2 grams. All right, 2 grams. And we're going to put that in the beaker. We're also going to get the mass of a flask, and so we're going to get our product in here as well, and then we will get that mass of product by subtraction. All right, so the flask has a mass of 93.8880 grams. 93.8880 grams. All right, and then we're going to get our product in there, and then we're going to weigh it again, and then we will have our mass of our product. All right, so this looks better for the separation. There's some white solid in there that I'm trying to get rid of. Okay, so now we have our product that we're going to then dry with our drying agent here. I'm going to wipe out the top. I always try to wipe out any grease that's in the top before I pour it out my product. I don't want to contaminate it, although we are going to distill it, so if it does get contaminated, we're going to purify it by distilling it. Alright, so now we take our liquid, we put it on a drying agent. Again, a drying agent, we're drying our liquid. All that means is we are taking the water out. A very nice smell. When you have your esters, esters are very fruity flavored. You have banana flavor. Yeah, I feel like I'm having a banana. It's a banana popsicle. Yes, anyway. Very, very nice fruity flavor. Alright, so we'll let that do its thing for a while. I'll set up the distillation with our weighed flask here. And here, we set this all up. Alright, so we will then decant into a very small distilling flask. Alright, so I just want to get the liquid, but again, if I get some solid, it's okay. We're going to distill the liquid over. The solid will remain. This will give us our boiling point and our yield. Again, by drying this, you're going to lose some product because I'm trying to get as much as I can, but that solid wants to come in, and I don't want that solid to go in. A little bit of solid in would be okay. I'm trying to not get very much, which is definitely going to hurt my yield, but try to block the solid. Alright, so that is the proper way to do a decanting, although you can see on the stirring rod it was just running down with the liquid. So we're going to have a little bit of our magnesium sulfate in there. Alright, so fine. We are not looking for 100% yield. We got some liquid in here that definitely should be able to separate from this. Alright, we're going to see how this distillation goes with this magnesium sulfate. Something I've not tried before. Decanting always seems to work a little better than this. Alright. Let's see how that goes. That is a lot of solid in there. All right, let's see what happens. Bottom at the top. Oh, we don't have it ice cooled. Let's get a couple ice cubes. All right, so now we have our ice cooled receiver. Not had a boiling chip. We do have a lot of solid in there, so you get a lot of bumping, and now you're going to probably find out what the term bumping means. With all this solid in there, I think you're going to get a lot of bumping. Yep, so there's the bumping. So you see the popping of the white going up on the sides. We definitely don't want the white to come over. So if our product has white in it, that would be not good. It's not what we want. All right, so this distillation is going to have to go a lot slower, so since we have all the solid in there. We want to get all the liquid to come over. We want the solid to remain in this side. And so I'm doing a little indirect heating, hoping to get less bumping and just boiling up the liquid iron. So we've got some product coming across, and our boiling point is at 20, 40, 60, 88 degrees Celsius. Over pretty nicely. All right, we may have to redistill it. We're at what we got now, 102 degrees Celsius. All right, it says to collect it between 80 and 115. Yeah, we don't want the white going up that high. Alright, so it looks to be all dry now. Kill the liquid is gone. Alright, now we just have to dry out. Final. Yeah, the temperature was starting to come back down because no more vapors were going up. Look at our product. Hopefully it's not too cloudy. All right, no, it's a nice clear, colorless liquid. That's exactly what our product is. It smells very nice. So the smell also tells me we definitely have our ester. All right, so now all we need is a actual yield. All right, and so we have 96.4080. So 96.4080. So I don't know, 2.5 grams ish. All right, was our yield. All right, that's the end of the Fischer Esterification.